Humanity has been fascinated by the number pi. As early as ancient Greece, Archimedes developed a method to approximate it. In the 18th century, Lambert proved that pi is not a rational number, it's irrational, and in the 19th century, Lindemann went even further and proved that pi is transcendental, not algebraic. It goes beyond ordinary numbers. So, how do we actually prove that pi is transcendental? Let's find out. The method is proof by contradiction. We assume that pi is algebraic, and then push that assumption until it breaks. If it leads to a contradiction, then pi cannot be algebraic. It must be transcendental. That's the basic idea of the proof. So, how do we find the contradiction? This is where Lindemann used a powerful result called the Lindemann-Weierstrass Theorem. Once you understand what this theorem says, the rest of the argument is much easier to follow. So, let's take a closer look. Suppose we have several distinct algebraic numbers, that is, numbers which are roots of polynomials with integer coefficients. Now, raise the mathematical constant e to those numbers as exponents. We can form a linear combination of these exponentials like this. Here, the coefficients are algebraic. Here's what Lindemann-Weierstrass theorem says. If that linear combination equals 0, then all of the coefficients must be 0. There's no other way. In other words, exponentials with base e and algebraic exponents cannot satisfy any non-trivial algebraic relation. That's the essence of the theorem. And this is what leads us to the conclusion that pi is transcendental. Let's return to our assumption that pi is algebraic. Multiply pi by I. Since I is a root of the polynomial x squared plus 1 equals 0, I is algebraic. Because algebraic numbers are closed under the 4 basic operations, I pi would also be algebraic. And here comes the famous identity with I pi and e. E to the power of I pi plus 1 equals 0. Euler's formula. In this equation, the number 1 can also be written as e to the power of 0. So, here we have two algebraic exponents, I pi and 0, with base e. This is exactly the kind of situation where the Lindemann-Weierstrass theorem applies. According to the theorem, the only way such a relation could hold is if all the coefficients are 0. But in Euler's formula, the coefficients are clearly 1. That directly contradicts the theorem. We've reached a clear contradiction. Why did that happen? Because our initial assumption that pi is algebraic was wrong. So pi cannot be algebraic. Pi must be transcendental. That completes the proof. But what else is there to discover about pi? What are you still curious about? Let me know in the comments below. And don't forget to subscribe for the next math travel. Thank you.